Hello and welcome to the virtual open house at Fraunhofer IMM. In my presentation I will cover the construction of a flexible electrochemical microreactor we developed here at the IMM and its application to the electrosynthesis of fuels and aromatic-free paraffins as a contribution of power to chemicals. As you can see, electrochemistry is a wide field with many applications, and today I will be focusing on the electrosynthesis part. At the end of the presentation we will go to the laboratory where we show you the production of aromatic-free hydrocarbons from a fatty acid mixture in aqueous solution in a laboratory setup using the Kolbe electrolysis. As a personal introduction, my name is Niels Baumgarten and I studied chemistry at the Johannes Gutenberg University of Mainz, and I'm now a PhD candidate at the IMM since November last year, working on the evaluation of electrochemical microreactors for electroorganic synthesis. My supervisor, Dr. Athanasius Ziogas, is responsible for the development of electrochemical microreactors here at the IMM and has expertise in online and process analytics. So why is it interesting to use a microreactor for electrochemical synthesis? Well, at first we have a very defined mass transfer, and this homogeneous and laminar flow we have in those microchannels creates a very narrow distribution of residence times. The high surface to volume ratio ensures a good heat transfer, and hotspots or overheating, which occur due to Joule reaction heat or high amperage, is avoided. In addition, we have very homogeneous electric field in those microreactors, so a very equal current density distribution. This results in a very high selectivity for the reaction. And finally, the low voltage drop, which is due to the small distance of the electrodes. As you can see here, due to the reduction, we have the reduction of the electrolyte volume and the compression of the diffusion layer here. We can do the reaction with a low concentration of conducting salt or without any conducting salt, and we can lower the energy consumption which is needed for the reaction. So first, some history and some expertise we have at the Fraunhofer IMM with the development of electrochemical microreactors. We developed a electrochemical microreactors called ELMI here first without an integrated heat exchanger at the beginning, and later on with an integrated heat exchanger or a cooler here, as you can see here, and later on with also some insulation and an integrated heat exchanger. We also had some industrial projects where there's divided cell resulted here with the synthesis of peroxodisulfate with a BDD electrode, so boron doped diamond electrode. We had also some EU project where we developed a thin layer segmented cell for screening setups for doing reactions in parallel and do some screening reactions, and also some other electrochemical microreactors depending on needs and depending on the different projects here. Concerning current user requirements and the experiments in the field of electrochemical microreactors we have at the IMM here, we developed a concept for a novel flexible electrochemical microreactor based on a plate stack design approach. Those black bars here represent the electrode plates with an integrated heat exchanger where the heat exchange medium can flow through, and the microstructured channels in between those electrodes creating an electrochemical cell. Depending on the position of the electrode, so an end electrode or an inner electrode, the electrodes are microstructured on both sides or just on one side. The vision was now a concept that allows the operation of one cell as well as the expansion to a larger number of electrochemical cells, increasing the throughput up to a production or industrial scale just by adding electrodes to the stack, as you can see it in this animation here. The operation in a monopolar or a bipolar way should be feasible. It should be also possible to integrate diaphragms or membranes to perform reactions that need a divided cell, as well as the integration of plain electrodes, which would again enlarge the number of electrochemical cells. Finally, the electrochemical microreactor could be used as a screening reactor in parallel, just by integrating insulation between the electrochemical cells. So firstly, some simulations were carried out to visualize and optimize the fluid flowing through the electrochemical microreactor. As you can see on the left hand side, there is a simulation on the electrolyte velocity along the channels, and on the right hand side we also see the temperature distribution of the electrolyte on the electrode surface. It is also interesting to consider the heat exchange medium. On the left hand side you can see the pressure drop profile of the heat exchange medium, and on the right hand side you can see the temperature profile or the temperature distribution also on the integrated heat exchanger or the electrode as itself. And the target was of course to have an equal distribution of the fluid flows in the end and have a constant temperature, and in the end a low pressure drop over the fluidic pathways. Here you can see a picture, a CAD picture of the electrochemical microreactor. This electrochemical housing is the assembly of the electrodes, and you can press those electrochemical cells together with this press here. So we do not need any screws. This is a big advantage of an easy upscaling reactor, and we can use PTFE seals to prevent the leakage between those electrodes here. The electrodes are processed in a selective laser melting process, so additive manufacturing, and are afterwards coated with PTFE to ensure insulation on the not active area. It is also after that fabricated with a side milling cutter to manufacture those micro channels, and they are after that plated with platinum, so it's in galvanostatic deposition of platinum, and that depends on the reaction need, so it is also possible to deposit the electric active area with other metals. In this picture you can see now the real reactor with the housing. In the left hand side here, in the left hand upper picture, you can see the inlet of the electrolyte, the distribution channel then, and the micro channels which are plated with platinum. You can also see this PTFE coating in black here to ensure the insulation. In this housing here we can press the electrodes together, and we have the inlet of the heat exchange medium and outlet on the other side. We have inlet and outlet of electrolyte and also an electric contact here with these nuts. As you can see here, the electrodes have some holes here in between to really track the temperature between during the reaction with some thermocouples. As you can see here, we have a model of an electrode where I now will show you the distribution or the flow of the reaction medium or the electrolyte and the heat exchange medium. So we have an electrolyte flow coming inside the reaction or inside the electrochemical reactor here, and also the heat exchange medium. We have then the distribution of the electrolyte in this channel here, and depending on the electrode, so that means have we an intermediate electrode which is structured on both sides here, or do we have an initial end or an end electrode which is only microstructured at one side, we have the distribution here. After that the electrolyte flows through the microchannel, and at the same time the heat exchange medium goes through the heat exchange channel which is inside the electrode, so meaning we have this heat exchange medium flowing here. After then a collection in this collection channel of the electrolyte, and then this leaves the electrochemical cell at this point here. In the next slides I will show you some validation of the electrochemical microreactor with different electrochemical reactions. So first, the cation flow method. This method needs a very low temperature, so -72 degrees due to this cation intermediate here. However, for pre-investigations, the reaction was done with a smaller electrochemical microreactor from IMM to explore the low temperature conditions and operations. So as you can see here, we have a divided cell with the diaphragm and seals to prevent the leakage. And we need a cryogenic cooler because this electrochemical microreactor has no heat exchanger. And as you can see, we got very good results with rather good selectivities here. So after that, we did the reaction with our new electrochemical microreactor, and due to the heat exchanger and the high flow rate being 5 times higher in comparison to the smaller electrochemical microreactor, it was possible to increase the temperature up to 7 degrees Celsius. And according to the obtained conversion and yield, we could reach excellent selectivity for the reaction. Another application of the electrochemical microreactor is the synthesis of peroxide dicarbonate, where we used a boron-doped diamond electrode as an anode. What is interesting here is that we used very high flow rates, so 75 milliliters per minute, and the reactor was capable to do so. And another fact is that we had very high currents, so leading to very high current densities, leading 560 milliamperes per square centimeters. However, we were able to control the temperature due to this heat exchanger and could operate the reaction with 9 to 13 degrees Celsius, although we had very high temperature due to this high current density. In this plot you can see the color removal in percent after some time, so the discoloration of indigo by peroxidicarbonate, as a proof that the synthesis was successful in the end. So for the rest of the presentation I will be focusing on the Kolbe electrosynthesis, which we will also do or perform later on in the laboratory. Fuels and lubricants, as you can see here, which can be used in personal care, pharmaceuticals or food, are nevertheless desirable products nowadays. However, they are most likely extracted from crude oils, and those products after that include some so-called mineral oil aromatic hydrocarbons, and they are suspected of being potentially mutagenic and carcinogenic. So at the moment there's no real synthetic pathway to synthesize paraffins based on renewable resources or renewable raw materials. We at the Fraunhofer IMM have developed a process to do so we can use electricity as renewable resource, and renewable material also is vegetable oils, so that means the carboxylic acids or fatty acids that come from vegetable oils, and we can synthesize hydrocarbons, aromatic free hydrocarbons and fuels via the Kolbe electrosynthesis. And we develop this synthesis, or we are able to do this synthesis in water, so we can on the one hand lower the cost of this reaction, and on the other hand we can lower the hazardous. That means we do not have to use any organic, flammable or toxic solvent for the reaction, so we can do this in water. So to do so we can use the Kolbe electrosynthesis. The Kolbe electrolysis is one of the oldest electroorganic syntheses. It was first observed in 1834 by Michael Faraday when he studied the electrolysis of aqueous acetic acid. This reaction was then later on applied by Hermann Kolbe in 1849 for the synthesis of various hydrocarbons. As you can see here, we have the reaction pathway. That means we have the oxidation of a carboxylate or a fatty acid to a radical. This radical decomposes immediately via decarboxylation to an alkyl radical, which then dimerizes to the desired hydrocarbon we have. It is also a possibility that we have a disproportionation reaction leading to an alkane and an olefin. And as a competitive reaction, again, we have the non-Kolbe pathway, meaning that we have another oxidation step generating a carbocation, which can then react with nucleophiles to alcohols or esters or olefins in a elimination reaction. So the potential products are paraffins, fatty alcohols, fatty olefins, and fatty esters. And depending on the educts we use here, we have also the possibility of generating asymmetric dimerization or asymmetric blanched alkanes, which can be used in creams, for example, later on. So as I've mentioned before, we will do the reaction in water or an aqueous medium. So the problem that occurs is a rapid decrease of the solubility of the fatty acids depending on the chain length. So as you can see in this graph, we have the number of C atoms of the fatty acids here and the solubility. And if you look at the graph from methanol, we have only slightly decrease of the solubility. And if we are in water, we have an extreme decrease of the solubility of the fatty acids depending on the number of C atoms. So to improve this behavior or to improve the solubility, it is a possibility to create a basic environment by adding sodium hydroxide or potassium hydroxide, for example, so that the acids are present in a deprotonated state, and that, as you can see here, improves the solubility of the fatty acids. Another possibility to improve the solubility of the fatty acids, in particular of fatty acids coming from renewable resources like plant oils, which are long-chain fatty acids, would be the ethanolysis. Here you can see the representative ethanolysis of triolene, and as you can see, it is possible to generate smaller chain triglycerides here, which can then later on be saponified and used as educts in the Kolbe electrolysis. So here are different strategies to use ethanolysis, saponification or hydrolysis, and the Kolbe electrolysis in the end to produce hydrocarbons and fuels from renewable raw materials. This picture shows an experimental setup for the production of N-alkanes from a defined fatty acid mixture via the Kolbe electrolysis. So the EDACT solution is pumped through the electrochemical microreactor where the electrolysis takes place, and the reaction mixture is then afterwards collected in this column or tube here. This tube is connected to a 4-channel process micro-GC to detect the gases evoluting during the reaction and to ensure some process monitoring. The phases then, as you can see this picture a little bit better, are separating in the tube, and the lower phase being the electrolyte, that means potassium hydroxide, water and some small amounts of unconverted fatty acids can be reused or can be recirculated again. That means, as you can see it here, we can reuse or recirculate it and add some newly fatty acids to gain a continuous process. And the upper phase, being the organic hydrocarbons, can then be analyzed with a GCMS. So the GCMS analysis shows high selectivity for N-alkanes, so almost 100%, and small amounts of disproportionated products. So these olefins and alkanes here are coming from the disproportionation reaction, and we could not detect any non-Kolbe products. That means, although we are performing this reaction in a basic environment, which according to literature would prefer the building of non-Kolbe products, that means alcohols, esters or large amounts of olefins, we are able to only get Kolbe products. So this again emphasizes the advantage of an electrochemical microreactor in flow. So with a flow rate, we can control the residence time and use very high current densities to realize a process which is not possible in batch synthesis. Here's another example, namely the synthesis of paraffins with a high proportion of asymmetric branched alkanes. And those branched alkanes are, due to their properties, very important in particular for the production of creams or cosmetics in the pharmaceutical industry and in medicine. And as you can see here, we used very high or even higher current densities than before. We also shortened the residence times, so we were able to exceed the results from before concerning the selectivity for the alkanes here. So this again then points out that the residence time and the current densities are very crucial parameters for our new developed synthesis to control the products being formed. As you can see in this table here, it gives the possible products or possible product mixtures by Kolbe electrochemical carbon-carbon coupling from fatty acids or fatty acid mixtures. So through pre-calculated fatty acid mixtures, it is possible to produce tailor-made products equivalent to jet fuel or diesel fuel, which we could also show here. For that reason, it is planned later on to have a pilot plant with the heart of the electrochemical microreactor here. So after the chemical reaction we have, or electrochemical reaction, we have the separation of gas and liquid in this part here, and after that the separation of the phases, so meaning that we have the hydrocarbons which are analyzed with a GC, so it is also possible to do later on online analytics, and the separation of the phase here, the separated aqueous phase, can be then reused again with some fatty acids added, depending on the converted quantities, that we have a continuous process later on in the end. In summary, the advantages of electrosynthesis have been demonstrated by the development and validation of a novel electrochemical microreactor. The modular design shows a very high degree of flexibility, and the electrochemical microreactor can be operated at various temperatures and pressures. We were able to develop a new process for the synthesis of hydrocarbons, of aromatic-free hydrocarbons and paraffins using the Kolbe electrolysis. So we can use renewable resources, being electricity, and renewable raw materials, that means fatty acids coming from vegetable oils or plant oils, to synthesize those aromatic-free hydrocarbons. We were also able to do the reaction in water, which will of the first reduce the costs. At the other hand, it will reduce the hazards because we do not need any organic, flammable or toxic solvent. In the end, we developed a process where it is simple and cost-efficient direct storing of energy in high-quality products. Finally, I would like to say thank you for your attention. If you have any questions or concerns, feel free to contact me or my supervisor, Dr. Athanasius Siogas, via email or phone. And now I would like to invite you to follow me to the laboratory where I will perform the Kolbe electrolysis with a new electrochemical microreactor. So, hello to the laboratory of fine chemicals. My name is Niels Baumgarten and I'm a PhD student here at the Fraunhofer IMM for almost a year now. Here you can see the electrochemical or the electroorganic synthesis of hydrocarbons via the Kolbe electrolysis. This is the electroorganic setup. As Athanasius said in the presentation, this is the iron press where the electrodes are pressed together and where they can be assembled. So as you can see here, we have microstructured electrodes in between from both sides, and the end electrodes are just structured from one side, as you can see here. We have also thermocouples where we can detect the temperature, and we have these inlets and the outlets for the heat exchange medium as well, as you can see here where we have the heat exchange medium. As a counter electrode we use stainless steel. This is coated with nickel to prevent any corrosion during the process. The electrodes do not need screws, so this modular design is very flexible. We can easily scale the reactor up or down and use several numbers of electrodes, and they are the leakage is prevented with seals in between the electrodes, and we can press them together so that we have a complete system. We have as educts water, fatty acids and potassium hydroxide. The potassium hydroxide is for conductivity at the one hand. At the same time, this deprotonates the fatty acids to ensure the solubility of the fatty acids in water. The fatty acids we use here is pantanoic acid, isonanoic acid and some saponified rapeseed oil, because in the future it is planned to do this with waste or with vegetable oils coming from renewable resources. We use some smaller chain carboxylic acids to enlarge the solubility of the longer ones. So now to pump or to do the reaction, we pump this reaction mixture, which is some kind of solution or emulsion, and stirred all the time with a HPLC preparative pump to the electrochemical microreactor. As you can see, we have a distributor here and we use small diameter to come in the reactor, and also at the other hand, which you can really see, we have a small diameter to realize some pressure drop. This ensures that we have a uniform distribution of the solution along the microchannels, and we have also the evolution of gas, which is carbon dioxide and hydrogen in this reaction, which is a very high amount of gas, and we try to avoid the coalescence of those gas bubbles, that those gas bubbles block the electrode and we have a problem later on in the efficiency of the whole process. The product then is collected in this tube or column here, where there's a lot of foaming. We have also a micro-GC, which is a process micro-GC, 4-channel process micro-GC, which can detect the gases, which are carbon dioxide and hydrogen, and some gaseous byproducts, hydrocarbon byproducts. And after we wait some time, we will see that the phases will separate, meaning the gaseous phase, the hydrocarbon phase, later on you will see it, and at the bottom the aqueous phase, which we can then reuse again, and due to concerning the converted quantities, we can add some fatty acids and some kind of realize a continuous process. Okay, so we start the reaction now. I control the power supply with the PC and have also the preparative HPLC pump to transport the electrolyte through the electrochemical microreactor. So as you can see, we have at the beginning a growing of cell constant or cell voltage and cell current until it adjusts when we have the stationary state. And this power supply can be operated in a constant voltage mode or constant cell mode. That depends on the goal of the experiment or on the set of parameters before. As you can see here, the product is collected in this column here. We have a gaseous phase, we have the organic phase and the aqueous phase. The separation takes some time, but the gaseous phase is analyzed via a micro-GC, where we will see carbon dioxide and hydrogen. This is also the main reason why we have this foaming and this extreme gas evolution, due to the fact that we have carbon dioxide coming from the decarboxylation of the oxidized carboxylic acid and hydrogen coming from the counter reaction. So after we stop the reaction, it takes some time until the phases are separated. I use now the electrochemical cell here to show it in a better way. I think you can see that we have the hydrocarbons being hydrophobe and having a lower density are at the top of the solution, and the reaction mixture consisting out of water, potassium hydroxide and some not converted fatty acids are here at the bottom, and they can be used in our next process with some added fatty acids depending on the converted quantities. We can then take a sample of this hydrocarbon and measure this via Gcms, so a gas chromatograph which is coupled with a mass spectrometer. This is not possible now to do it online, however in the future it's planned to do this analysis online later on. So now we can take the sample of the hydrocarbons and this can be analyzed, like I've said before, with a gas chromatograph. To do the first online analysis, like I've said, we use a process micro-GC 4-channel where we can detect the gases, which are at the most cases hydrogen as the counter reaction, carbon dioxide, which evolutes due to the decarboxylation of the oxidized acid. We have only just a few detection here of oxygen that comes mainly from the solution, from oxygen that is solved in the solution, or from oxygen from the air. Only a few parts coming from the electrolysis, showing that we have a very selective process and do not oxidize the solvent. In addition, we have also some butan and butane. These are side products and come from pentanoic acid, which are side products in the Kolbe electrolysis as well. So I hope you enjoyed the demonstration here, and we can show you what we are able to do with the electrochemical microreactor. If you have any questions, concerns, or are interested in other products or other possibilities with this electrochemical microreactor, feel free to ask me or my colleague Athanasius, and we will thank you now for listening.